So if you look at classes of problems, the easiest problems are flat plate problems. So basically, if you have flat plates that are a constant width into the board, then if you have a vertical plate, then the pressure at the top of that vertical, if this is a free surface, so this is at the surface, and so because the top of the plate is at a free surface, the pressure is 0 there, and the pressure here is some gamma h, so you have a triangular distribution. Here's another flat plate, constant width. Again, it comes up to a free surface, so the pressure is 0 there. The pressure here is gamma h, again, it acts perpendicular to that plate, but it's a triangle because it comes up to a free surface. Same with this guy. This is a flat plate, comes up to a free surface, the pressure is 0 there, gamma h here, so it's a triangle. So if a plate comes all the way up to the surface, the pressure at the top is 0. But if you're interested in the pressure on a plate like a gate in a dam that's submerged some distance, then the top of this gate is at some h1, the bottom of the gate is at some h2. Then the pressure at the top of this gate is gamma h1. The pressure here is gamma h2. So now you have a trapezoid. And so anytime you have a straight plate, constant width, that's some depth, no matter what orientation, whether it's straight or whether it's... So if this is your free surface, and you have a vertical plate like this guy, or you have an angle plate, or you have a plate that goes back into the page this direction, again, your free surface is up there, then this is gamma h1, gamma h2. This is gamma h1, gamma h2. This is gamma h1, gamma h2. And so whenever you see a plate that's submerged, it's going to have a trapezoid on it. And in a few minutes, I'll show you the formulas. There's kind of standard formulas. In the past, when you looked at distributed loads and you had a trapezoid, we would typically divide this into this guy and this guy. And you can still do that on these problems, but because trapezoids come up so often in fluid pressure problems, I actually have a formula page in the notes that summarize some of the distributions that you see a lot. And so for flat plates that extend to the free surface, you have a triangle. The area of that triangle is 1/3 base times height. And the base is now pressure. So this is a pressure, this is a length, and then but it's super important that you don't forget the width into the page. So read the problem carefully. It'll say the dam is 10 foot wide, or it'll say consider a 1 meter slice, or consider a 1 foot slice. And so then you just treat it as one. But these are formulas for a triangle. For a trapezoidal distribution, for a flat plate that doesn't come to the surface, then the area is the average of P1 and P2 times the length, and again times the width into the board. Don't forget the width. The centroid of a trapezoid is 1/3 of 2P1 plus P2 divided by P1 plus P2, and all of that times L, which is the length of the plate. And you just should remember these formulas or have them written down because, again, they occur a lot. So those are flat plates. Now curved surfaces. And so pretty much anytime you see a flat plate, just put a trapezoid or triangle on it and you're good to go to get FR. But a curved plate, let's talk about curved plates. When you have a curved plate, the pressure distribution looks like, well, I've already drawn it. It basically looks like this guy. It's like, how do you find the volume of that? What do you do? And so what you can do is resolve these guys into horizontal and vertical components. And you say, how does that work? How does that work? I'm glad you asked that question. So basically the way that works. So this is a force exerted by a fluid on a horizontal plate. So if you have a free surface here, and you have a plate down here with some area, and at some depth, h, okay? And there's fluid up to the free surface. And so basically there's a pressure distribution that acts on this plate. And what are these pressures? They're gamma h. So these guys, pressure is equal to gamma h. And basically the plate is flat, and so the depth is constant. And so the resultant force, the Fr, is equal to the pressure times the area, which is equal to gamma times h times area. But what is h times area? H times area is the volume. This guy is equal to the volume of the water, or the fluid, above that plate. So if you take this column of fluid from wherever that plate is, all the way to the surface, the volume of that column is the cross-sectional area times h. And so the same Fr is equal to basically the weight of the column of fluid. So that's a vertical force. And then we've already talked about the horizontal. And so the horizontal, on any surface, the horizontal is always going to be a triangle or a trapezoid or whatever else. So that's the horizontal. So let's look at a curved surface. So if we basically take a curved surface, and you go, I can't find the pressure distribution on that guy. But if you take that curved surface and discretize it into discrete horizontal and vertical steps. And so if you basically go and of course you can shrink these steps to infinitesimal size. On each of these horizontal surfaces, there's a vertical force that's acting downward above this guy. And there's a vertical force here, and there's a vertical force here, and a vertical force here. And all of those vertical forces are equal to the weight of the fluid above that horizontal step. But now you can take these vertical guys, the risers, if you're talking about stairs, these are risers. And so each of these, so if you see a pressure distribution that looks like this over the whole face, this much of it acts on this guy, this much of it acts on that guy, this much of it acts on this guy. And so the sum of all these guys is F horizontal. The sum of all these guys is F vertical. And that's why it works. That's where the formula comes from. And so in general, if you have a curved surface, the weight of the fluid above the curved surface is the vertical force. And it acts at the centroid of this area. And the horizontal force is basically the same horizontal force that would act on the cross-section of this dam, which basically in general is like a triangle if the dam comes up to a free surface. If the curve is submerged, then you have, so if this is your free surface, you've got a dam element here, and then you've got a curved surface here. And we're interested in the resultant force just on this part of the guy here. Then we just have a trapezoid here, which is this much. So the F horizontal is a trapezoid. And then the vertical on this guy is W1 and W2. And so this total weight and this total weight. And so the vertical force is from this plate all the way to the surface. The horizontal is just this trapezoid, because it's just this trapezoid that acts on the cross-section of the curve, okay? And so that's how the horizontal and vertical works.